students, my name is Mr. Abiy Antana. Welcome to grade 11 mathematics unit 1, which discusses about relation and function. In this unit we'll try to cover about a power function. Mainly we'll try to discuss on the properties of a power functions in relation to their exponents. We'll define what's power function, and we'll try to state some properties of a power function in relation to exponents. And also for a given power function, we'll try to see a technique how to determine domain and range of power functions. Then finally, graph of some power functions. What looks like a graph of power functions. So let's start from the first. So it's important to know the definition. A power function is a function that can be expressed in the form of f of x equals to ax the power of r, for a must be different from 0 and for any real number r. R can be any real number, but a must be different from 0. So these are some of examples of a power function. X to the power of 3, 2x to the power of minus 3 over 2, and h of x equals to x to the power of minus 1 over 3. So for those power functions, we'll try to determine some properties of a power functions in relation to its power, and we'll try to determine domain, range, and what looks like a graph of some power functions. Okay, power function of the form f of x equals to x to the power of n, for n is a positive integer. So for this form of a power function, we'll try to see in two different cases. The one when exponent of n is even integer, like x to the power of 4, x to the power of 6, x to the power of 2. The coefficient can be any number. Here, when the exponent is even integer. So what's domain of such power functions? A domain meaning what possible values of x can be substituted. So every real number defines this function, or every number can be substituted in place of x that can define. And range of this function depends on the power n. When every integer the power of 4 or even integer, whatever x is negative, x is positive, x is 0, the output value, the range is always greater than 0. So we can generalize for any power function of the form f of x equals to x to the power of n, for n is even integer, domain is the set of real number, and the range is non-negative real number, or y greater than or equal to 0, because any number the power of even integer is non-negative real number. And a graphs of f of x equals to x to the power of n for even integers looks like this. Look, the domain is every real number, and the range is non-negative real number or positive real number including 0. So to the right of y-axis, the graph is above the x-axis, which implies for positive value of x, corresponding value of y is also positive, and for x is to the left of y-axis, the value of x is negative, but the value of y is positive, which is above the x-axis. So for any real number x, the output value or the value of y is non-negative real number. And the graph of f of x equals to x to the power of n for even integer looks like this. Then case 2, a power function of the form f of x equals to x to the power of n for n is odd. Now, when the power of x, n is odd integer, we'll try to determine its domain, range, and what looks like a graph of such power functions. So these are some of examples: x to the power of 3, x to the power of 5, x to the power of 7 for odd integer n. So domain of a power functions of the form x to the power of n for odd integer is the set of real numbers. It's possible to substitute every real number, meaning the function is defined for any real number, and the output value, the range is also real number. When we cube negative numbers, the output is negative number. When we cube positive numbers, the output value is positive number. When we cube 0, the output is 0. So, the range is also the set of real numbers. And what looks like graph of such power functions? Look, a graph of f of x equals to x to the power of n for an odd integer n. For an odd n implies for an odd integer n, the graph looks like this. For a positive x, the value of y is positive. For a negative x, the value of y is negative. Because negative number, the power of odd is a negative. So, graph of a power function of the form x to the power of n for an odd integer n looks like this. Then the other one, what if the power is 1 over n? Here also we'll try to consider two cases. The first one, for even integer n, f of x equals to x to the power of 1 over n, which is equivalent with f of x equals to the nth root of x. These are some of examples. F of x, the square root of x. G of x, the fourth root of x. H of x, the sixth root of x. So now, to determine domain and range, what determines domain of such power functions? The index or n determines domain of such power functions. Here, the square root of 2 implies the index is 2. If the index is even integer, the radicand must be non-negative real number. What is the radicand? This x must be greater than or equal to 0. This must be greater than or equal to 0. So to determine the domain, what restricts the domain now? The index. If it is with even index, the radicand must be non-negative real number. That is, x must be greater than or equal to 0, and the range is also greater than or equal to 0, because the square root of 0 is 0, the square root of a positive number is positive real number. So for a power function of the form f of x equals to x to the power of 1 over n, where n is even integer, domain is non-negative real number, range is also non-negative real number. So what looks like the graph? Let's see. Look the graph now. The graph of a function f of x equals to x to the power of 1 over n, where n is even integer, looks like this. It looks like this. It starts from 0, so it extends to the right. It extends to the right. Then what if the power 1 over n for n is odd integer? So case 2, for odd integer n f of x equals to x to the power of 1 over n, which is equivalent to the nth root of x. So this is the index now. N is the index. So example of this function, f of x cube root of x, g of x equals to fifth root of x, and h of x equals to the seventh root of x. If the index is odd number, the radicand can be any. It can be positive, it can be 0, it can be negative number. So we can substitute any number in place of x. So a domain of this power function is the set of all real numbers. And the range is also the same. A range is also all real number, because the cube root of a negative number is negative, and the cube root of a positive number is positive, and the cube root of 0 is 0. So a range is also the set of real number. Okay, so graph of a power functions of the form x to the power of 1 over n for n is odd looks like this. It looks like this. it extends to the right when the value of x is positive. The nth root of x is positive. And when the value of x is negative, the nth root of a negative number is negative number because n is odd integer. The other one, a power function of the form f of x is the power of m over n. Now we'll consider the ideas before as a fact and we'll extend that idea. If both m and n are odd integers, what will happen if both are odd integers? So it looks like this. F of x equals to x to the power of 3 over 2. G of x equals to x to the power of 5 over 3. In general, f of x equals to x to the power of m over n equals to the nth root of x to the power of m. Now, since both integers m and n are odd numbers, this index is also odd. If the index is odd number, the radicand can be any. It can be any. Even this can be represented by the nth root of x, then the power of m. So if you remember from the above result, the nth root of x, domain of the nth root of x is the set of real number when n is odd integer. So we can substitute any real number in place of x. So real number, the power of some odd integer. Negative number, the power of odd is negative. Positive number, the power of odd integer is positive. 0, the power of odd integer is 0, which describes the output value of such power functions is the set of real number 2. So domain is the set of real number and range is also real number. So properties of this function is the same as a properties of graph of f of x equals to x to the power of 1 over n, where n is odd integer. That is the above result, what we have discussed on the above slide. Okay. A power function of the form f of x equals to x to the power of m over n, when n is even and m is odd. Look, when m is odd and n is even, f of x equals to x to the power of 3 over 2. So if we need to express in radical form, the square root of x cubed. Now what is the index? If it is the square root, we can understand the index is 2. The square root of x cubed. So what is domain of such power functions? Since the index is even integer, we can rewrite this the square root of x the whole cube. No problem, you can write, but most of the time the index 2 is not written in the square root form. So even no problem if you write the square root of x the whole cube. So this is even index, the square root of x. So what numbers can be written in place of x? Only non-negative real numbers. Because the square root of negative number is now defined in the set of real number. So x is non-negative real number. So the square root of a positive real number is positive real number and the square root of 0 is 0. So what could be the output or the range? The cube of non-negative real number is also non-negative real number. So the domain is x greater than or equal to 0 and the range is also y such that y greater than or equal to 0. And look what looks like a graph of power functions of the form f of x equals to x to the power of m over n, where n is even and m is odd. Now we have two graphs. The one it bends upward, the one it bends downward slightly. The difference, whenever the power m is greater than n, the output value is greater than the input value. For example, look this, for the power of 3 over 2, the input value is 4. So what could be the output value? It is the square root of 4 then the whole cube. That the square root of 4 is 2, then cube it's 8. So the output value is greater than the input value. So it will bend upward as it goes to the right. And when m is less than n, the graph slightly bends downward. Look, we can rewrite like this. Even we can write for the power of 1 over 2. No problem. What is the input value? It's 4. So what could be the output value? It is the square root of 4, which is 2. Now the output value is less than the input value, so it will bend downward. Then the other one, a power function of the form f of x equals to x to the power of m over n, when n is odd and m is even. Example, f of x equals to x to the power of 4 over 3, which is a cube root of x to the power of 4. And equivalently, we can write it's a cube root of x, then the power of 4. Now, what could be domain and range of such power functions? The cube root of x, if it is the index, we have seen on the above slide, the cube root of x. So for such power functions, the input value can be any real number. The input value can be any real number. So domain is the set of real number. But here the power is 4. Whatever this value is positive or negative, it's the power of 4. So when the exponent or the power is 4, the output value is non-negative real number. So the range of such power function is y such that y greater than or equal to 0. And we can look what looks like a graph of such power functions. Look this. Graphs of f of x equals to x to the power of m over n, where n is odd and m is even. Now, there are two graphs, the red and the blue one. What makes this different? The first one, it bends more upward when m has larger magnitude than n. Like when m is greater than n. And the second one, it bends downward. This one, when m is less than n. Then power function of the form f of x equals to x to the power of minus m over n, when the power is negative number, how we can determine domain and range. Domain and range is the same as a power function of the form f of x equals to x to the power of m over n, except the denominator must be different from 0. Because if we have such power functions, f of x equals to x to the power of minus m over n, if it is a negative exponent, we can rewrite in this form 1 over x to the power of m over n. So here in this expression, the denominator must be different from 0. But all properties what we have discussed before holds the same. So domain and range is the same as power function of the form f of x equals to x to the power of m over n, except the denominator must be different from 0. So we'll add this additional point to determine domain and range of a power function. Now look, determine domain and range of each function. Then the first one, f of x equals to x to the power of minus 2 over 3. So to determine domain of these, look, we can rewrite it's f of x equals to, since it is a power function with negative power, we can rewrite 1 over x to the power of 2 over 3. Let's add one further. It's equal to 1 over the cube root of x the whole square. Okay, now what's domain of this function? Domain equals to a set of real number that defines or that makes through this given function. So since the index is odd, the cube root of x, So what numbers can be substituted in place of x? Every real number can be substituted in place of x. But since this one is the denominator, x must be different from 0. So domain is real number except 0. Real number except 0. And how we can determine range? This one is real number except 0. If we square it, what could be the output value, the range? Range of this function, range equals to real number square, meaning if it is negative, the square of a negative is positive, the square of a positive is positive. So range of this function is the set containing y such that y greater than 0. Good. Then similarly, let's determine domain and range of this function. G of x equals to x to the power of minus 3 over 4. So in the same way, let's write 1 over x to the power of 3 over 4. And fractional exponents can be expressed in radical form. The fourth root of x the whole cube. Now, what is domain of this function? It's the fourth root of x cube. 1 over the fourth root of x the whole cube. Now, what numbers can be substituted in place of x? Since it is the fourth root of x, x must be non-negative real number. And since it is a fractional expression, the denominator must be different from 0. So, numbers that can be substituted in place of x must be greater than 0. So, domain, the set containing x greater than 0. And the output value, the fourth root of x, and x is a positive number, the fourth root of a positive number is positive. So positive number cube is also positive. So range is also the same. That's y such that y greater than 0. So this is range of this function. So you can do more examples which are related to the examples, the point that we have discussed above. So from this discussion, we have covered how to determine a power function, domain, range, and we have seen some power functions, what the graph looks like. So domain and range depends on the power. So the range depends on both n and m. If a power function x to the power of m over n determines the domain. Because when n is even, x cannot be negative. If n is odd, x can be any number. So, n determines domain of a power function, but the range depends on both n and m. So, power functions are important in many areas of mathematics and science and are used to model a wide range of phenomena from population growth to a behavior of substance. So do more examples, exercise to develop concept or a power function, about power function, basically how to determine domain, range, and what looks like a graph of a power functions. So this is all about the lesson. See you next time. Goodbye.